In this video, we'll discuss the relationship between rectifiability and densities. The main result we'll discuss is Preiss's theorem, which states that radon measures M rectifiable if and only if its M-dimensional densities exist and are positive and finite almost everywhere. We have basically been working for several weeks now on proving one direction of this theorem. And in fact, all the tangent measure techniques we've discussed were introduced in one paper to solve this problem. So why is this result so interesting? Well, it's because we have a simple measure theoretic condition that a priori says nothing about the geometry of the measure, but from that simple measure theoretic condition, we actually get some explicit geometric information. So in particular, our density condition here only says that the measure of any ball center at almost every point is asymptotically equal to a constant times its radius to the power m as the radius of that ball shrinks. But from this asymptotic information about the measure, we obtain the structural property that says that we can parameterize the support of the measure by Lipschitz mappings, i.e. that it's rectifiable. So let's first show how the reverse implication goes. So this will be the culmination of the results from the past few weeks. So if the densities exist and are positive and finite almost everywhere, we've seen from our discussion of tangent measures that this implies that all the tangent measures are m-dimensional flat measures at almost every point. And now Marstern's rectifiability criterion, which we covered in the previous video, says that this condition implies the measure is rectifiable. So now for the remainder of the video, we'll sketch the ideas for how to prove the forward implication that being rectifiable implies the densities exist. So first I claim that the forward implication of Preiss's theorem follows from the following special case. So suppose that we have a set gamma that's equal to the image of Rm under some Lipschitz map F. Then not only do the m-dimensional densities of Hausdorff measure restricted to the set exist almost everywhere, but they're actually almost everywhere equal to 1. So let's show how the forward implication of Preiss's theorem follows from this result. So let's suppose we have a m rectifiable radon measure mu, and let's suppose that the above lemma is true. Let gamma be some Lipschitz image of Rm, so we'll show that the m-dimensional densities of mu exist and equal some positive constant at mu almost every point in the surface gamma, where this constant depends on the point x. Now, because mu is m rectifiable, it can be covered by a countable union of such Lipschitz images. So if we prove this property for one Lipschitz image, that will imply that this property holds mu almost everywhere. Now, recall that being rectifiable also means that mu is absolutely continuous with respect to Hausdorff measure. So in particular, if we restrict both these measures to gamma, we see that mu restricted to gamma is absolutely continuous with respect to Hausdorff measure restricted to gamma. And thus, that means that mu restricted to gamma can be written as some measurable function g times Hausdorff measure restricted to gamma. So now for Hausdorff measure almost every x in gamma, and hence for mu almost every x, because mu is absolutely continuous, we can apply the Lebesgue differentiation theorem and the above lemma to show the following. So let's look at the m-dimensional density of mu bxr over 2r to the m. Okay, so this is the same thing as theta m mu of x. Okay, now by Lebesgue differentiation theorem applied to the measure mu and to the set gamma, we know that this is equal to the limit as r goes to 0 of mu bxr intersected with gamma over 2r to the m for almost every x for mu almost every x in gamma. Okay, but now the measure of this ball restricted to gamma, this is the same thing as the limit as r goes to 0 of 2r to the minus m times the integral over the ball bxr of this function g, d Hausdorff measure restricted to gamma. Okay. Now I'm going to rewrite this slightly. So this is the same thing as the limit as r goes to 0. So I'm going to replace this with Hausdorff measure intersected with gamma divided by 2r to the m. So basically what I'm doing is I'm multiplying and dividing by Hausdorff measure of this ball restricted to gamma. And so now I get an average integral here. Okay? But now, almost everywhere, I know that this ratio, so notice that this is just hm gamma x, which is equal to 1 almost everywhere. And then this average integral, by the Lebesgue differentiation theorem, I know that almost everywhere, this is just going to converge to g at x. So this equals 1 times g of x. So this is equal to g of x. And I can show that mu almost everywhere, this number g of x is positive. So the number c of x here is just g of x down here. And so thus, I've shown that at mu almost every point in the surface gamma, that the density, the m-dimensional density of mu exists and equals some positive constant. So now what remains to show is this lemma. So recall that for sets of locally finite m-dimensional measure, the upper densities are at most 1 almost everywhere. So that means that it suffices to show that the lower densities are at least 1 almost everywhere, since then the combination of these two inequalities will imply that the m-dimensional densities exist and equal 1 almost everywhere. Recall that Sard's theorem says that almost every x in gamma is the image of some point y under f where the derivative of f has full rank. So we're going to assume that x is one of these points, and we'll show that for almost every such point x, the lower density is at least 1. By translating the function f in its, or composing f with a translation in its domain and its image, we can assume with thought loss generality that x and y are both equal to 0. And notice that this implies that f of 0 equals 0, so f fixes the origin. So why can we do this? So notice that if we prove that the lower density is at least 1 at the origin, then when we translate, this does not affect the value of the density because we have not changed the shape of our set gamma. So we're only changing the image of f. We're only changing the set gamma by isometries. So that means that if the lower density of this translated version of gamma is at least 1 at the origin, that will mean that the lower density of gamma at the original point x is also at least 1. So that's why with thought loss generality, we can assume that x and y are both 0. Now, additionally, we can assume with thought loss generality that the derivative of f at 0 is equal to the identity, where by the identity in this case, we really mean the n by m dimensional matrix, n by m matrix made up of the square m-dimensional matrix I sub m followed by a bunch of zeros. So this is a linear transformation from Rm to Rmn, where it fixes points in Rm. Okay, so why can I do this? Recall that by singular value decomposition, I can write df of 0 as a composition of a orthogonal transformation on Rm, a n by m diagonal matrix sigma, and a m-dimensional orthogonal transformation V. So if I look at the function f that I get by composing on the left with u inverse and on the right by v inverse, then the derivative at the origin by the chain rule will equal u inverse df at 0, v inverse, and this will equal this diagonal matrix sigma. And recall what it means for a sigma to be diagonal matrix is that it's equal to some square diagonal matrix followed by a bunch of zeros, so that the resulting matrix is m by n. So thus, if I take this function and compose it on the right now with the inverse of this diagonal matrix, okay, then I get that this is equal to the identity 0, which is this identity matrix here. So notice that dm inverse exists exactly because I'm assuming that I'm at a point where my original derivative df of 0 has full rank. Okay, and notice again, just like before, these compositions of f are not changing the shape of the image of gamma. So in particular, so notice that when I compose with this diagonal matrix on the domain side of f, that doesn't change the image of f at all. The only change in the image of f under these transformations is when I apply this rotation u inverse. But again, this is an isometry because it's an orthogonal transformation. And so it's not changing the shape of gamma. It's not changing the shape of the image of F. So thus, if I prove that the lower density of this rotated version of gamma is at least 1 at the origin, that will also imply that the lower density of the original image of F is at least 1 at the origin. And that's why I can assume without loss of generality that df at the origin is equal to this identity transformation. And finally, I can assume just by scaling my function f that the Lipschitz constant is at most 1. So again, this will not affect the result of the theorem. So here in this diagram, this outer ball denotes the m-dimensional ball center at 0 of radius r contained in Rm. Okay? And this blue region here depicts the image of this ball as lying in Rn. Okay? So notice that this image lies in the higher dimensional space Rn, so you should imagine this in this picture that we're looking down on the space Rm from Rn, and this blue region is lying slightly above or below the ball, but only slightly, since for r small enough, f restricted to this ball is approximately the identity mapping. Okay, so in particular, the image of the boundary of this ball, so this darker jagged line here, the boundary of this image, or the image of the boundary of this ball under f, is only a small perturbation of the original boundary, okay? And in particular, as r goes to 0, f will look more and more like the identity mapping, so that the image of the boundary is getting closer and closer to the boundary of the original ball. So hence, the projection of the boundary of image of the boundary of this ball, okay? If we look at the orthogonal projection of the image of this boundary, that will enclose a smaller ball, so whose boundary is this dotted line here. And in particular, we can make it enclose a ball center at 0 of radius 1 minus epsilon r, okay? So loosely speaking, we're taking a large piece of blue cloth and stretching it out so that the boundary of the cloth encloses this smaller ball, okay? But if the boundary circles this ball, that means that the cloth must lie over this ball. Or in other words, if we take the orthogonal projection of the ball center at M of radius 0r, this contains the ball, m-dimensional ball, center at 0 of radius 1 minus epsilon r. Okay, so this was sort of a hand-wavy proof. But in the notes, I show the actual details, which require a bit more algebraic topology, but hopefully this gives some indication about why the result should be true. Okay, so let me make some room here. So assuming this containment now, we can now get an estimate for the lower densities. So the lower density of gamma at 0, so this is equal to the lim inf as r goes to 0 of the Hausdorff m-dimensional measure of the ball center x of radius r intersected with gamma over 2r to the m. Okay, now recall that f is 1 Lipschitz, which means that the ball center at 0 of radius r intersected with gamma contains the image of the m-dimensional ball center at 0 of radius r over 2r to the m. Okay, now by this containment here, so the Hausdorff measure of this set is at least the Hausdorff measure of the orthogonal projection of this set. Okay, and then by this containment here, this is at least the lim inf of the m-dimensional Hausdorff measure of the m-dimensional ball center at 0 of radius 1 minus epsilon r over 2r to the m. And then we know exactly what the Hausdorff measure of a ball is in Rm. It's just going to be twice the radius, which is r to the m, over 2r to the m. So we can see after simplifying, this is just equal to 1 minus epsilon to the m. And so thus, we have that the lower density at the origin is at least 1 minus epsilon to the m for all epsilon less than 0, bigger than 0 that we want. So if we let epsilon go to 0, that implies that this is actually at most 1. And that finishes the proof.